In the mountains of northern India, an engineering masterpiece called the Chenab Bridge has just been completed, setting a new world railway record at a height of 359 meters above the riverbed. To easily visualize the scale of the main character in today's video, if you place the Eiffel Tower of Paris at the bottom of this gorge, its peak would still be 35 meters below the bridge deck. But for the engineering team, the figure of 359 meters is just the tip of the iceberg of a massive mechanical problem. What truly concerns them is not the height, but the wind, an invisible force with speeds up to 266 kilometers per hour, always ready to turn this 30,000-ton steel structure into a fragile ribbon in midair. How do you keep a train running stably on this massive arch structure when even the rocks beneath its foundation are not entirely stable? Before we begin, don't forget to like and share this video to support us in making more new content. And now, let's get started. The Chenab Bridge is not just a height record, it is the vital link of a 272-kilometer railway line, connecting the Kashmir Valley with the rest of India. For centuries, this region was almost completely isolated in winter due to heavy snowfall and landslides. A seamless railway line through the Chenab Gorge is the only solution to maintain the economic and security lifeline for the border area. However, this is a land with absolutely no access. At the beginning of the project, there were no roads leading to the bridge's foundation site. The only way to bring massive machinery into the construction site was for the engineers to start with a prerequisite task: carving a road into the cliff face. They began by cutting deep into the mountain to open more than 26 kilometers of specialized mountain roads. This was an extremely dangerous journey where workers had to swing on ropes in midair to drill rocks right at the edge of the deep gorge. But the real challenge was not just the vertical terrain. It was the nature of the rock in the Himalayas. The geological strata here are cracked and layered like a pile of crumbled cookies. If traditional blasting methods were used to clear the road, the shock waves would collapse the entire mountainside. To solve this, they applied the pre-split blasting technique. Instead of one large explosion, thousands of small drill holes were arranged to place very low-yield explosives, creating sharp cuts along the cliff without damaging the core structure. Right after the rock was removed, the cliff face was covered with steel mesh and sprayed with high-pressure concrete to lock the rock surface, creating a stable support base for the future steel arch structure. Once the access problem was solved, another challenge immediately appeared: how to transport 30,000 tons of steel through these narrow and treacherous mountain passes. With a terrain featuring a jutting cliff on one side and a deep abyss on the other, transporting monolithic bridge girder structures is extremely difficult and carries the risk of horrific accidents. To safely bring materials to the site, engineers had to break down the entire massive volume of steel into moderately sized modules, small enough for trucks to navigate through the sharp curves. At the same time, right at the material gathering point near the edge of the gorge, engineers set up a special fabrication workshop. Here they welded and assembled the scattered steel pieces into complete bridge girders, ready for the most important phase: reaching out into the open air. When all preparations were complete, the bridge officially entered the field construction phase. Because the steel arch structure is the heart of the project, aimed at completely neutralizing the massive wind pressure, the very first task was to create an unchangeable foundation deep within the mountain. The process began by using explosives to strip away thousands of tons of rock, creating flat surfaces on the vertical cliffs. Right after that, engineers drilled dozens of meters deep into the rock to install high-strength cable anchors and pump high-pressure grout to fill every geological crack. The final step was pouring over 34,000 cubic meters of concrete to form two massive gravity foundations. These foundations not only anchor the bridge's legs, but also act as the point to receive and neutralize all the compressive force transmitted from the steel arch, turning the natural cliff into a super load-bearing system. At this point, many viewers will surely wonder, why go through the trouble of building this complex arch structure and massive foundation system instead of the modern cable-stayed bridges commonly seen? The answer lies in the aerodynamics problem. Inside the V-shaped gorge of the Chenab River, the wind is compressed to form swirling gusts with speeds up to 266 kilometers per hour. A cable-stayed bridge with a thin deck would easily be twisted by these hurricanes and cause dangerous resonance. Choosing an arch structure is the most optimal solution. With absolute rigidity, the arch structure transmits the entire wind pressure along the steel curve, pushing it straight into the two concrete foundations firmly embedded in the mountain. This is the art of borrowing nature's force to protect the structure itself from nature. As soon as the two gravity foundations were completed and rooted in the cliff, the next crucial phase was launched, building an aerial operating system to assemble the arch bridge. Because the gorge is so deep, using conventional cranes is impossible. Engineers installed two giant crane towers on both sides of the abyss to stretch the world's largest steel cable network connecting the two peaks. These cables act as an aerial railway, the only lifeline to deliver materials out into the middle of the gorge. Each section of the arch bridge, previously broken down for transport through the pass, is now hoisted up and slid across this cable system. The arch assembly process is executed using a symmetrical method. The two halves of the arch reach out simultaneously from both sides of the cliff. To prevent the structure from collapsing before it can be connected, a series of pre-stressed cables are used to anchor each girder segment to the mountain, creating an extremely complex bracing network in the middle of the windy gorge. Only when the two halves of the arch meet at the exact center and are securely locked with a high-strength bolt system is the skeleton of the bridge officially complete. At this point, the arch structure is capable of self-supporting and ready for the next stage, installing the vertical piers and launching the deck onto the back of the arch. This is the final step to transform a simple steel skeleton into a true traffic artery in the heart of the Himalayas. First, engineers proceed to erect the vertical piers, steel trestle piers, along the length of the bridge arch. These piers are assembled from prefabricated steel segments, acting as transmitting arms that guide the entire load from the deck down to the steel arch system below. Each pier must be placed in an absolutely precise position to ensure compressive force balance for the entire structure. After the pier system is securely fixed, the deck launching phase begins. Instead of assembling small sections in the middle of a risky abyss, engineers chose a safer solution, fully assembling the steel girders on solid ground at both ends of the bridge. Under the pushing power of massive hydraulic jack systems, the thousands of tons steel block begins to be incrementally launched out into the air, slowly sliding over the prepared pier tops. This process requires strict control over speed and thrust, because every meter of girder extended is a time the arch system undergoes a real load test. When the final girder segment is successfully connected in the middle, the bridge is no longer scattered pieces. A solid steel plane has officially linked the two mountain peaks, ready to welcome the first trains crossing the gorge at a world record height. After more than 20 years of relentless construction with many ups and downs, the final result has materialized. On February 20th, 2024, the first test train officially rolled across the Chenab Bridge. This is not just a simple technical inspection, but a historical milestone marking the complete connection of the US BRL railway line, making the Indian dream of piercing through the Himalayas a reality. Few know that to achieve this persistence lasting 2 decades, the project received strong approval and commitment from the highest leadership level. It was Prime Minister Narendra Modi who pushed this project as a top national priority, viewing it as a symbol of the Make in India spirit and a testament to the infrastructure engineering autonomy of the billion-people nation. But to truly understand the full value of Chenab, we must place it next to its biggest current rival, the Huajiang Canyon Bridge in China. Both share a great goal: connecting isolated lands to modern civilization at unimaginable heights. Yet why is Huajiang expected to take less than 5 years to complete, while India had to trade off 20 grueling years? This is not just a battle of numbers, but a clash between two engineering philosophies. On one side is China, the master of speed and process optimization. Previously, I made an in-depth video analyzing how the Chinese construct the Huajiang Bridge so lightning fast, and you can find that video in the description below. As for Chenab, the Indians chose absolute stubbornness and defensiveness. They accepted spending 2 decades to cast massive foundations and stuff concrete into the steel arch core, turning the bridge into an indestructible fortress in the heart of the Himalayas, capable of withstanding explosions and magnitude 8 earthquakes. My perspective is, if Huajiang represents the power of modern construction technology and dizzying development speed, then Chenab is the symbol of sustainability and ironclad patience. One chooses flexibility to adapt, the other chooses solidity to confront time head-on. In your opinion, between a steel fortress enduring 20 years of construction and a speed marvel completed in 5 years, which bridge is truly the greater legacy for future generations? Leave your thoughts in the comments section below. Thank you for joining me on this journey to dissect this mega project. Don't forget to check out the video about the Huajiang Bridge I linked in the description for a more multi-dimensional perspective. Hit like and subscribe so you don't miss the next superstructures. Goodbye and see you next time.